cement connected. That's what you want. Hydration products to be connected and water to be disconnected. And you can take different shapes and find out what the percolation threshold. These are all volume fractions, okay? These are all volume fractions of percolation. Okay, so some cement hydration stories here. So if I say one cement grain has some C3A and C2S. Somebody asked a question, how do you ensure you have all these different things in cement grains, right? A couple of days ago somebody asked. So just show an example. Assume that this grain is only C3S. Assume that this grain has C3S and C3A and C2S. Assume that this guy is only gypsum. Right? I can do all of that. And then what is all this blue? Whenever you see blue, it's the ocean, right? It's all water. Now, after some time, half an hour, you have ettringite that is formed, right? Ettringite consumes what to form? Gypsum and C3A, right? So you have ettringite that is formed. This C3A is gone, so that's why it's showing it as a void, because that gets consumed to form the ettringite. And then in this area, so you can have CSH gel that is being formed. Remember we talked about the topochemical reaction on the surface? So CSH gel, only half an hour, so very little CSH gel is formed. You can have CSH gel that's formed on the surface. At 4 hours, what happens? Way more of CSH gel, and then there is ettringite, there is some calcium hydroxide that is formed. Is the system percolated yet? Yes. I can go from here to here, water, from here to here, through water I can go completely, right? What happens after 672 hours, and that's what, 14 days, 24 times, no, 28 days. 672 hours is 28 days. After 28 days, see what happens? Lot of CSH, some unhydrated cement, there is some voids inside, there is calcium hydroxide, there is gypsum. Now, is a solid is percolated completely, and of course you can consider this to be water around, but then in this solid, solid is connecting itself completely, right? So, if you use that and use your image analysis, all the tools that I showed you yesterday, from images. Now, if I get a structure like this is basically a cartoon of an SEM. You see that? Basically a cartoon of an SEM image. I take an SEM image which I see all the different faces, and if I plot the degree of hydration as a function of fraction connected, very low degree of hydration, connected fraction of water is 100%. All of you good with that? As my degree of hydration increases, connected fraction comes down. Now, very important, look at this. What is this curve? What water cement ratio is that curve? 0.35. See that at a degree of hydration of about 0.6, I have zero connectivity between water, right? Doesn't have to be points, roughly at a hydration of 0.55 roughly, 0.58, 58. If I increase the water cement ratio to 0.45, how much of hydration do I need for that? About 0.72. If I increase the water cement ratio further to 0.5, I need a degree of hydration of about 0.85. Very, very, very powerful message is embedded in this picture. If you ever do a water cement ratio of 0.5, you are never going to get a percolated solid system, because for that case, what's the degree of hydration you need? 85%. You are not going to get 85% of your cement hydrated. You see that? You are now in trouble where if you have, and this is the real reason why you say, oh, increase in water cement ratio decreases the durability. This is why increase in water cement ratio decreases the durability, not because too much of water is bad for something else. You see here, you need 85% of degree of hydration of cement to close off all the channels that are available for something else to go in. And it's highly unlikely that you will get 85% of the cement to be hydrated. Whereas if you have a water cement ratio of 0.35 or 0.4, you need only lower amounts of degree of hydration. Which means When you have a lower amount of degree of hydration, remember your hard core, soft shell? When you have a lower degree of hydration, your harder core, more of your harder core stays put, which means your mechanical properties are going to be better. Okay, so that's a combination that you have to think of. Also look at the capillary porosity with fraction connected, with nothing connected. Even when you have nothing connected, complete solids, you still have about 18% capillary porosity. Now this number, this is about 18%. Okay, so remember this value of 0.18 or 18%. That 18% is what we call the percolation threshold in a cement paste. That 18% is the value where the solids are completely connected. So, if somebody asks you, what is the minimum porosity that I can have, maximum porosity that I can have still with all the solids connected, that has to be 0.18. Make sense? 0.18 for all the solids connected, even then you will have about 18% porosity. Get the idea? So you are effectively never going to completely avoid capillary porosity in concrete. So try not to attain the unattainable. Try not to say that I'll give you a concrete with a porosity of 10%. Okay, you might get it with the water cement ratio of 0.2 and with large amounts of fat mixtures and cement not hydrated. But it's not required for general purpose concretes. General purpose concretes, what you want is a connected solid system, and 20% porosity where the solid system is connected and the pore is not connected. So what? Leave it at that. But you do not want, like I said, to be looking for an 85% degree of hydration to get to that point, because 85% degree of hydration is going to be an unattainable thing in general, unless you make a bridge deck and pond that bridge deck for 1 year. Not let the traffic go through, put a dike on that, fill it with water for 1 year, then you get 85% hydration. If you cure for 7 days, forget 85% hydration. You're going to get 50-60% hydration at the most. And that 50-60% hydration, if you already have a higher water cement ratio, you are ending up with very, very high chance of durability loss very quickly. So basically what I'm trying to do is I'm trying to give you the theory behind everything that you're seeing outside. Okay? Now, it's not that people don't know what has happened. Right? Again, the same point that I've been telling you over the last 3 days. It's not about we not knowing what is happening. We see it. We see corrosion. We see cracking. We see delamination. We know what is happening. We know we think we know why it is happening. We say we have a bad concrete. But further deeper question, why is my concrete bad? Even when I try to do everything right. Yeah, I used a 0.5 water cement ratio for my concrete, and then I went on, I did everything well, I compacted it well, I vibrated it well, I covered it well. No, you're not going to get this anyway, right? So your contractor might say, I did everything that was the specifications. You're not going to get it because you haven't satisfied the most fundamental characteristics that is required to get you a good concrete. Right? So this is where microstructure connects with, so you're looking at what is happening at the micron level, and this connects to what is happening in the scale of a bridge deck or a building. See how the size scales that I talked about yesterday or day before, see how transcending of these size scales happen. And this is the most important point. So when you're doing research, try not to be prescriptive in any of your concrete. Again, I'll use the food example, right? When your moms taught you how to cook, my mom taught me how to cook because when I was going to US, I had no other option, I had to cook. So I took cooking lessons from my mom. My mom never said put 1 teaspoon of this, 1 teaspoon. It's all for taste, right? If you look at all those things, you put sugar, salt for taste. Who knows the taste? We know the taste, right? No, as far as food is concerned, your taste and my taste would be different. But as far as concrete is concerned, good concrete is good concrete for everybody. Bad concrete is bad concrete for everybody, right? performance becomes the most important thing, and microstructure governs the performance. I want to spend some time on this picture to give you the real essence behind why concretes fail, why durability is such a big issue, even though apparently, and there are a lot of concretes specified in India, and people say 0.5 water cement ratio is okay. You guys see that? I tell all the times, no, anything more than 0.4 is not okay, purely based on this part, this point. And then they'll say, no sir, we have put in 20% fly ash. Yeah, but out of that 20% fly ash, how much is reacting? Now, this is for a cement which you know can hydrate. How much of a fly ash can hydrate in a standard cement system? Very, very little. So if you're putting in fly ash, you get some initial benefits because of the density difference in packing, but then after you lose it, right? So if you use a fly ash and then use a higher water cement ratio, you are in the same situation still. So the control has to be in the microstructure, and that is why I keep emphasizing the point over the last 3 days that concrete is a material that has to be designed, not proportioned. We do mixture proportioning, we don't do mixture design. What is your proportioning? How much do I need to satisfy what somebody else wrote in a code? That is proportioning, right? Your cement content has to be this much, your aggregate content has to be this much, you still use all the charts. Have any of you got in their first, you all do concrete mixture proportioning based on M. S. Shetty's book or some book? You do all the proportioning using the specific gravity of aggregates, all of that. Have you ever gotten in the first trial the right thing that you proportioned? No. Then what you do? You adjust. Mistake. Any adjustment is a problem. Any adjustment is a compromise. You adjust for workability. You adjust for strength. You adjust for cement content. You adjust for slump. You adjust for air. You're compromising on all of those. At none of these stages are you designing the materials from the first principles. Right? So, first principle design. Does any of your concrete mix design talk about packing of particles? You kind of brush that aside by saying, I should have a good cumulative particle size distribution. What does a good size distribution mean? It means really nothing as long as you don't define what is good, right? So, you don't do packing, you just use, again, it's not essentially bad. So, these are all based on practices. Concrete is still treated as an art. Somebody, he can do very good concrete mix design. There's no reason why one can do good mix design and the other cannot, right? Do you say that he can do very good differential equations whereas somebody else cannot? Everybody can if you just have to learn it, right? Concrete is also a science. And there is this, and we want to get it, it becomes art or artless when you do it bad in the field. Until then, the science and art are really good. So, just want to make sure that, everybody good with this point? Please make sure that you understand this idea, and that's why I'm spending time on the effects of microstructure on what can happen in the long-term properties. Okay. Percolation, electrical response, I probably will skip some of those. Anybody interested in electrical testing? Okay, I can talk to you later. We don't have to spend everybody's time. Okay. So, just to give you maybe 2 minutes to talk about what electrical response is a lot of times there are certain tests that, for example, we talked about percolation and connectivity of pore size, pores for example, right? I gave you a lot of examples on using MIP to do, get images, use MIP, get threshold pore sizes, take derivative. We took SEMs. I showed you granulometry. You take these curves, you do these derivatives. I showed you that. So those are all ways of doing it. But how do I test it? But so these are all, think about how much time does an MIP experiment take. In a day you can do 4, 5, 6 MIPs. How much does image analysis take? Quite some time to prepare a sample and do images and all of that. So for a field guy, if I have a concrete in the field and I want to test it, I want to have some methods. So we want to look at what will be the right method. So one of the methods is using electrical properties. So basically what you do is you take a concrete, and it's becoming very popular in the US now, where resistivity and impedance based methods are used for quality control. You take a cylinder of concrete, after 14 days, 28 days, whatever is the time of hydration, you measure the conductivity of that sample. Conductivity meaning electrons are passing through it, right? Or ions are passing through it, or ions are conducting the electricity. Where are the ions in a cement paste? In the pore solution, the pores. So if the pore solution is very direct, between top and bottom is just one cylinder, the conductivity is going to be very high because the ions can conduct electricity very fast. Whereas the pore structure is really tortuous, the electrons will have to flow, the ions will have to conduct through all these tortuous path, your conductivity will be less. So you use that as a measure of how tortuous your pore structure is, and studies have shown this has very good connection with, and if you're interested, you can look at a number of my papers. Many of them are on my website. You can look at a number of papers that we have done to prove that in the field somebody can use these measurements to give an indirect estimate of what porosity, pore connectivity, all of those are. So for research, you can use this to make connections. For people in the field, they can use this as a template to find out what their properties are. So electrical properties are basically a good kind of test. Expensive instruments, but I'll skip. I want to talk some of this about, but it'll be more complication for you. Okay, relaxation of water. I'll skip this part. It'll be in your notes if you ever want to see all of that. I mean, there is dielectric response, percolation. Now I'll show you one slide that I probably will okay, here. Effective conductivity, electrical conductivity that I measure with a lot of samples, without fly ash, all of that, okay, at different times, because porosity changes with time, right? And I plot that with porosity. You see, I get a trend like this and a trend like that. At what point are they intersecting? Point? And what did I say is importance of 0.18? That is the level of connectivity of pores that you can afford when all the solids are connected. I showed you that 0.2, close to 0.2 value in the previous slide, right? Where is that? Oh, I come this far? This one. Oh, no, previous one. This part, right? 0.18. So you get effectively through electrical conductivity, electrical measurements, you get exactly what you get from an image-based, actual image-based scenario. Okay. So 0.2, and then show you a few more when you have different times, how the dielectric constant changes with porosity and all of that. Okay. So we have about 20 minutes before the 20 minutes you can sit and meditate, sit and talk, sit and listen. I can start the next topic. It's up to you. Yes. Correct. We call it. Yeah, yeah. No, percolation doesn't mean permeability. Percolation just means connectedness. That's what it is. We talk about percolation permeability as one thing because when the pores are connected, water comes through. But percolation doesn't have any relationship with flow. Percolation just means connectedness. So if I take red balls, white balls, green balls and throw it in this room, in this area, I can still say that I have a percolation of white balls if I can connect all white balls from one end to the other. Right? So percolation just means, in fundamental physics, percolation. I know. that is. So there is new Samsung has something called Bixby. Have you guys seen it? So Bixby is your voice assistant, right? Like Alexa and what's that in iPhone? Siri. So Bixby. So I told something similar to Bixby. So she thought I'm calling her. And please tell me what you want. Okay. But because it doesn't recognize anything that's similar to Bixby, it says, okay, please tell me what you want. So percolation basically is nothing but connectivity. You had a question?
People normally say permeability detects a durability, and people do find the permeability by various different tests, including the water permeability. Can you comment on the most appropriate method to test permeability?
Okay. So permeability, how do we define permeability? Ease with which something flows through something. That's permeability, right? Normally water. Normally water. So, but again, you can't make that. That's why I said why do we call permeability? Normally water. But do you have a rapid chloride permeability test? Are you permeable? Is that doing permeability of water? It's chlorides, right? So permeability is nothing but ease the flow of anything through something else. Water generally, because water is something that we know flows. And there are a lot of permeability tests. Now, if you want to look at transport, I wouldn't use the word permeability, I use the word transport always, which means, so when I say permeability, I am implicitly saying that I am forcing the fluid flow either through gravity, right, mostly through gravity, or some external pressure, but still gravity included in it. But transport through concrete happens through several different mechanisms. There is absorption, there is adsorption, there is wicking, there is diffusion, there is permeability. All of these mechanisms transport water and something else through concrete. Permeability is the easier thing that we measure. So you see that elaborate water permeability apparatus that you can use with pressure and all of that. I hate that method. You actually get some good numbers when capillary porosity is all that you are worried about, right? So and which is most of the time true. So if I know I am a poor concrete maker and I want to somehow show that even with my poor concrete making, I still do reasonably well, you use that test. Because you avoid all the other long-term mechanisms which are much more influential, like diffusion, right? So if you make a good quality concrete, if you say that I've controlled my water cement ratio, I've had good particle packing, you don't have to do permeability, because once you go below a certain porosity and pore size, every concrete that you test will give you the same permeability, because this test can't distinguish between any of that. So for really good concretes, that's not a test. Okay? So if you do a 0.3 water cement ratio concrete, I'll say thank you very much. Why am I bothering about putting all this? It takes a lot of time, right? To put all the pressure through this and finding out where the level of water is and all of that. Why bother? Don't need it. Rapid chloride permeability is another dirty test. It's an extremely bad test, and in the US we are slowly eliminating it. It's very hard because contractors, testing labs love it. Why? In 6 hours you have the result. In 6 hours you have the result, and you have this beautiful numbers. Silica fume companies are the ones who don't want to stop that test, because silica fume will look wonderful in that test. I'll tell you the reasons for that also. Okay? So silica fume will make concrete, if you have a silica fume in concrete, this test will make that concrete way better than it actually is. Okay? So silica fume manufacturers love this test, and again, there are a lot of lobbies and all of those, so they don't want this test to be stopped. But really, rapid chloride permeability test is pushing chlorides from an area of higher concentration, what's 2% or 3% sodium chloride, to an area of lower chloride concentration, which is your sodium hydroxide solution, right? All of you know that test. From sodium chloride through to sodium hydroxide through concrete. How? By applying what voltage? 60 volts. Now think about 60 volts. What do you normally do with 60 volts of potential? Get a bulb. What happens if you have 6 hours of a 60 volt bulb burning on? What happens if you touch it? Lot of heat, right? Right? You haven't tried touching a bulb when it is burning for 6 hours? No? You don't, right? Because you know it's hot. It's going to be very hot. Same thing. So what is it going to do to the concrete? Heat it up. It's called joule heating. You heat the concrete up. What happens when you heat something up? Well, you have this pore solution and you heat it up. What happens when you heat it up? You will have, no, it doesn't evaporate at 60